Okay, so the last few classes you have actually been seeing various applications, right, where interaction between fluid and particles come into the picture. So so such situations, many of times you might have used certain relations, certain empirical correlations, and so on. So most of them you might have actually dealt with complex geometries. What we are going to do today is to look at flow situations which the geometry can be simple, but the flow can still be complex. So when I say the flow being complex, I actually meant turbulent flow. Okay. So earlier part of the course, we have really looked at what is laminar flow. In various geometries, you have been able to really solve the equations in an exact form, and you have been able to calculate what is the velocity profile, what is the pressure drop, and so on. So we are going to look at slightly different situation now, where the flow itself become complex even if the geometry is very simple. So that's where the turbulence comes in, and we are going to see how turbulence comes, what can we do when your fluid flow is turbulent, what is the best that we can do so that you can go ahead with designs. So that's the idea now. So so let's say let's take any simple case. Okay, let's say you have flow between two parallel plates. So that's where we actually started our class. We have let's say two plates, and there is a fluid flow in it. And let's say you are interested in finding out what is the velocity. Okay, and to find out velocity, you're going to do an experiment, and you are going to put a probe, a velocity probe, to measure velocity at a particular point, let's say. So there is a fluid that's flowing, okay, and let's say you want to measure at some location what is the velocity. Okay, so you have put a probe into that system, and then the probe actually gives you what is the value of velocity. And you are plotting that velocity as a function of time. So you are continuously measuring the velocity and plotting it. Okay, so we will assume that the flow is steady. Okay, so there is a constant flow rate through the system. So if you plot velocity at that point, let me just denote it using u, at some random location as a function of time. Okay, if the flow rate is very low, okay, so when I say flow rate is very low, that's really characterized by low Reynolds number. Okay, so if you define a Reynolds number, and if Reynolds number is sufficiently small, we'll see how small it is. It's a small, but let's say if Reynolds number is very small, and you have put the probe and you measure the velocity and plot it as a function of time, if the flow is steady, you're going to see that the curve is going to look like that. Okay, velocity is not changing as a function of time, so you'll get just a straight line. Now let's say you increase the flow rate. Okay, when you increase the flow rate, what happens to Reynolds number? It's going to increase. So let's say you keep increasing your Reynolds number, but you continue to measure it. So this is what happens if Reynolds number is small. Okay. Now, beyond some certain Reynolds number, okay, what you are going to see is that if you measure the velocity, it will more or less be constant, but in between you will see some fluctuation. Okay, and then it will again come back to a constant, and then again there will be a burst, and then again it's going to come back to its constant value. Okay, there will be sudden bursts in the flow at various points. We don't know a priori when it is going to happen, how it is going to happen, but that's what you see. You don't care. You will further increase the Reynolds number, let's say. Okay, so this is some intermediate Reynolds number. Now you go to really large Reynolds number, and large Reynolds number would really mean that your flow rate probably is very high. Okay, if you do that, where you will measure velocity as a function of time, you would see that it's just a random signal. Okay, something of that sort. Okay, there is nothing like you are not going to see anything constant about it. Okay, even though you can see that there is a mean which is constant, but it's really going to be a noise. Okay, because the velocity is continuously changing in time. So the left hand picture, when Reynolds number is very small, that's when we call the fluid flow is laminar. Okay, and the right hand side, when the Reynolds number is very large, when you see this noisy signal, you will call the fluid flow is turbulent. And in between, when you see this, it's actually the transition from laminar to turbulent. So this is what we have as a laminar flow. This is what we have as turbulent flow. And this is when we have transition between the two. And remember, this is not with respect to time, okay? This is with respect to Reynolds number that I am talking about. Is that okay? So let's just see what it looks like. You might have already seen several instances. So you have heard about Reynolds experiment, right? So what you have is, I don't know, I think this is actually a pipe, okay, where the fluid is flowing. The fluid, I think, I don't know why one way or the other. And the blue line that you see is basically some ink that you have inserted. Okay. So what would you expect if the fluid flow is laminar? That ink is just going to be carried along with the fluid flow. Okay. But if the fluid flow is very turbulent, then the fluid will see this fluctuating velocity. Sorry, the ink will see this fluctuating velocity. So the ink will start actually spreading to different regions. So that's what this experiment is. Let's just watch it. So I think initially, so on the right hand side corner, you can see the Reynolds number. So Reynolds number is 355. Now they are hiking up the Reynolds number, so the flow becomes sort of unstable, but it's still smooth. Now this is basically the transition, okay, where you start seeing some burst. The flow rate is increasing, you can clearly see that now the burst become completely dispersed, okay. So that's basically the turbulence. I'll just play that again. So it doesn't look like a pipe because the Reynolds number seems to be very small. Yeah. What is that? Diffusion will happen, but diffusion will happen over a very small time scale, very large time scale, because diffusion is a very slow process. Okay, so if there was no fluid flow, you would have seen that of course the ink is basically, getting diffused, but you are not letting that to happen. Your fluid flow is sufficiently bigger than that. Okay, so laminar, that's transition. And there goes the turbulence. Now, we can actually see it in quite a lot of situations. Yeah, let's just check this out. So this is fluid flow, okay, that's coming from a pipe, and then you must have seen this, right? When you open it very lightly, you basically have a very thin, thin stream that's coming, and that will look very clean and neat if the water is actually clean, okay? But if you start increasing, then you will see that it basically becomes hazy, okay? So that's nothing but laminar to turbulent flow transition. So yeah, so he's just going to put the finger, I think, you can see that clean stream, okay, and therefore you will be able to see the finger if you look through that, okay. That's because there is no velocity fluctuation, everything is like a laminar, it's basically a laminar that's flowing down. But if you increase the flow rate further, hope he shows that. Maybe I chose the wrong video. So anyway, you could try that. I think this might show. No, this is also same. There it is. This is a nice one. There you see. Okay, so on the right hand side you see the laminar flow, and on the left hand side you see the turbulent flow. So, so the so even in a pipe, okay, in an industry, this is exactly what you are going to see. Okay, so what we have done so far, okay, let's say we calculated the pressure drop in a pipe, right? We derived nice relations, but all those are useful when the flow is laminar, but not when it is turbulent. So there's a clear distinction. You can see that visually, but now mathematically also that's going to be a distinction, and therefore we need to know what is the velocity profile in a pipe when the fluid flow is turbulent. Okay, so our objective now is going to derive an expression for that, so that we can calculate what is the pressure drop and therefore come up with the right pump, so that you can pump fluids. Okay. Yeah, so for a pipe, typically this Reynolds number, okay, where the laminar to transition happens is approximately when Reynolds number is 2300, when Reynolds number is defined based on the diameter, which is d, v is some average velocity, rho divided by mu. Okay, so you could define Reynolds number based on radius, diameter, anything. So when it is defined based on diameter, and when it is approximately slightly greater than 2000, you would actually start seeing the transition. So just to give you what are the typical regimes. It can start forming those bursts. So before that, you can almost certainly say that the flow will be laminar. So it must be either because the fluid, this may not be a cylindrical pipe. Okay. Now the other thing is that it's very sensitive to external disturbances. Okay, any small vibration is sufficient to basically make it up. So if you want to exactly find 2100 or 2300 in a lab, you need to basically make sure that everything is vibration free and so on. Otherwise, it will pick up. So it must be one of those reasons. And it should be sufficiently far from your inlet and so on, and what is also there at the outlet. Yeah. So just to characterize the regimes, so 0 less than Re less than 1. So Reynolds number, okay, is what is going to characterize it. In that regime, if Reynolds number is very small, the flow is very viscous, and one another name that you use is called creeping flow. Okay. So if Reynolds number is between, let's say, 1 and 100, the inertia of the fluid is going to become important, but still you are going to get a laminar flow. So this is basically strong inertia, but the flow will still be laminar. Between 10 raised to 2 and 10 raised to 4 is you have the transition to turbulence. In fact, you could have one more in between, let's say 10 raised to 3, because 10 raised to 3. So this is where you have again strong inertia, but something called laminar boundary theory is useful. And let's say if it's between 10 raised to 3 to 10 raised to 4, this is when you have transition to turbulence. And when it is 10 raised to 4 to 10 raised to 5, this is turbulent. and this is, one could say, I'll explain moderately, Reynolds number dependent. Okay, so the equations that we had used earlier, okay, the ones which we derived are strictly for a laminar flow, and when the flow is laminar, so this is the regime that we really have talked about, okay, the equations that we used. But typically when you go to large scales, you are going to deal with large pipes, large flow rates, and the flow invariably turns turbulent, and therefore we ideally would like to go to larger Reynolds numbers, but and therefore we would really like to go somewhere there. Okay, so we need now equations for that. Just to mention that this let's say the one it's in between. Okay, this is still laminar flow, but you need there is something called a laminar boundary layer theory, which we probably will just touch upon towards the end of the class. So such theories are very useful in that Reynolds number regime, and this one. Okay, the transition to turbulence, there are, it's very difficult to do either theory or experiments in that regime, and typically what you do is you just avoid doing any design in that regime. Okay, so when you do it, you either stick to laminar flow or you stick to turbulent flow where you have some knowledge of it. Okay, in between if you come, rather you basically change your parameters such that you can do a better design with either of the flow regimes. So that's what it is. So we want to go to that green highlighted one now. Okay, any questions? So we talked about head loss. You remember? What was head loss? Yeah, go ahead. Something where you actually had a pipe, you were, let's say, fluid is flowing from one side to another, and you wanted to characterize what is the pressure drop that is, through a pipe, for example. So we probably would have taken some pipe, we said, okay, you have fluid that's flowing, and then there is a pressure drop of delta P, and we would have calculated HF, the head loss, as delta P divided by rho G plus some delta Z. If you want, you can turn your pages and check that the relation is correct. Okay, so if delta is Z, that means if there is no difference in the elevation, okay, between two ends, it's just related to the pressure drop itself. Otherwise, it's the fact that the effect of gravity will help. Okay, so that's where that delta Z is coming in. So HF is nothing but really a measure of the frictional losses. Okay, so the moment you know HF, that's what you can prescribe, and that's what you can actually use for your design. So the idea is typically to calculate what is HF, the head loss. Okay. Now the way we did it is we basically defined something called a friction factor, and we wrote down some relation between friction factor and head loss. How did it relate HF into F? Das is friction factor. Something of that sort. Okay, and then we would have finally related our friction factor to Reynolds number, that. Okay, so the idea of doing this thing was that you specify the Reynolds number, that will tell you what is friction factor, that will tell you what is the head loss. Okay, so this is really this way that our calculation should go. Okay, but though we derived it the other way. Okay. Now, this calculation that we have done is for laminar flow, and therefore, we would want to repeat this calculation for a turbulent flow. So, there is a challenge. So, the velocity profile that we saw, right, it was very noisy, it was highly fluctuating. Okay. So, what do we do with that? So, let us say we again have flow somewhere, okay, flow in a pipe for example, and let us say the flow is turbulent. That means the velocity, okay, the flow is no more unidirectional, you can't really say that. So, if you have it, okay, and the velocity is highly fluctuating, that means, and if I call let us say this direction as x, so typically we will write down the three components of velocity u, v and w, okay. So, we have u, v and w, and in this case what is going to happen is that u will be a function of x, y, z and t, okay. Similarly, v is also going to be a function of x, y, z and t, w is also going to be a function of x, y, z and t, and even the pressure is going to be a function of x, y, z and t. You measure any of them, you are going to see that fluctuation, okay. So, that tells that the governing equations that we used, right, we can't do all those simplifications that we had used earlier. So, we need to invent something better. So, can we invent something better is the question. So, let us just write down, let us say the continuity equation and the momentum conservation equation. These are the two equations that we had, and we just kept on manipulating that. So, continuity equation in Cartesian coordinates was just dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. And we had the momentum conservation. Let us just write down the x momentum equation. That is the x momentum equation, right. When do we say something is a solution to this equation? When that expression satisfies this equation. For example, we had the parabolic profile. If you substitute that profile into this equation with the right boundary conditions, you will find that it basically satisfies. Okay. Now, what is the kind of solution that we are looking for in a turbulent flow? We are looking for a equation which basically is going to do like this. Okay, we are going to look at a fluctuating kind of a expression, okay, an expression which is fluctuating. And as of now, we have no idea, or we do not know any equations that can actually predict like that, or that can be represented with a completely fluctuating field. Okay. So, therefore, it is basically useless to look for a solution which is going to predict exactly those fluctuations, because at the moment we even do not know, but we can't give up, right, we need to do design. So, what is the best that we can do? So, this person Reynolds, right, who did this Reynolds number experiment that you are familiar with, is there something interesting about that statement? No? Okay. So, see, he came up with this idea called Reynolds averaging. Okay. What he said is this: let us say you have a flow which was that, right, this one on the right hand side, where the velocity field was continuously fluctuating. We are saying that, okay, we do not know any function that can exactly prescribe those fluctuations, but why should we care about? Let us only worry about a mean value, because we are only interested in the mean value. So, let us write down everything in terms of a mean velocity, because that is what is going to interest us. Okay. So, that means we need to define a mean velocity from an exact velocity. So, we have u as a function of time, which is highly fluctuating. Okay. We said, all right, we will define a mean velocity and worry about a mean velocity. How do we define a mean velocity? u, let's say mean, is equal to, I'll say I'll integrate it from some 0 to t u dt, and then I'll divide it with the time interval, right? So basically I have taken a time t, okay, a sufficiently long interval that I will keep on adding the velocities, and then I add up all of them and divide with my time period. I am going to get my average velocity, right? So that's the u bar that I will have. So therefore, one says that, okay, so therefore my total velocity at any point is going to be my mean velocity plus a fluctuating velocity, correct? So u is the one that satisfies the equations. What we are interested in calculating is u bar, and the difference between u bar and u is what you call the fluctuating velocity. That's all right. Similarly, you can define a V bar, W bar, P bar, everything, okay? A mean pressure, mean velocity, and so on. What would be U prime bar? So, what is U prime bar? Mean of fluctuating component. What do you think that would be? It should be 0. So, let's prove that is equal to, by definition, it's 1 by t integral 0 to t u prime dt, that's equal to 1 by t integral 0 to t u minus u bar dt, that's equal to 1 by t integral 0 to t u dt minus 1 by t integral 0 to t. So, u bar is a constant, so I can write it down outside, u bar dt, that's equal to u bar minus u bar is equal to 0. So, as expected, it comes out to be 0. How about u prime square bar? So, I am taking the square of the fluctuating velocity and averaging it. Will that be 0 or non-zero? It will be non-zero. Okay, and this distinction actually becomes crucial. Okay, so let's see where it leads to. Any doubts, by the way, till so far?